Hi everyone, my name is Dawer Jamshed. I'm the Chief Scientific Officer of Vertex Labs, and today I'll be talking to you about the trusted interpretation of machine learning methods. First off, why would we even care about improving model interpretability? One of the greatest benefits of machine learning has been that you could just feed in data along with the expected answer and it would learn for you without you having to learn and understand the inner workings. And that has seen quite a bit of success in spaces like tech and search engines and so on, but it really hasn't held up for us in our space where it's really not practical or feasible to deploy a model that you don't understand at all, right? It's not safe to prescribe drugs when there is no way for you to understand why you're saying that these drugs are okay to take. Following up from that is the kind of surprising idea of contestability. Sometimes you'd like to actually disagree with your model, but if it's only spitting out a prediction without any reason why, there's no way to agree or disagree because there's no line of reasoning with which to make arguments. And then beyond that, it's frankly way more useful to have a model that can also spit out an explanation. Imagine this. You just learned to play guitar and you've made your first song and you call over your friend, say, hey, please tell me if you like my new song. It's my first. You go ahead, play your song, and they say, no, I don't like it. Well, what do you do from there? You don't know why they didn't like it, so there's no clear way for you to improve, so you can perhaps go and play that song for many other people, but with slight variations to get a sense for what pieces they liked or didn't like. But that's super inefficient, and really it might still not get you the answer you're looking for. Alternatively, if your friend had just told you that they did not like the way you ended the song, or maybe some certain chord progression, that would instantly let you know how to work and improve on your system. This is true with machine learning too, right? If we have the ability to see why the model makes its decision and we want to say, hey, this is wrong, we can then actually improve the model because of the transparency, and vice versa. The model can help us generate hypotheses in our own research, improving overall knowledge discovery. Now that we're sure that we even want to make our models interpretable, what do we need to do that, and what does that even mean? Well, first off, you need to make sure your data is trusted. It has to be from a secure source. You need to know that it's good, it's clean, it's being monitored for any irregularities or changes, and that your problem formulation actually makes sense. Right? If your problem statement is flawed, no amount of interpretability will help you. But let's say we've done all of that. You have some sort of secure way to get your data. What next? Well, first off, inside of interpretability, there are two types. There is transparency and posthoc, which I'll get into in a little bit. And then beyond that, there is interpretability at the global level and interpretability at the local level. Global meaning the model's general behavior and understanding why it likes certain things or dislikes certain things, and then local meaning explanations of certain predictions. So transparency. What I mean by that is the interpretability that's defined during model specification. And in fact, it can and often does sacrifice quite a bit of predictive power. Let's break that down a little bit further here. First off, you can have simulatability, which is, can you actually think through what the model does? We're in the day and age that a model's internals are fully visible. You can see each and every computation that's being done. It is a computer. But that doesn't mean you can actually understand it in any reasonable amount of time. And you'll see here, I have two decision trees. This one on the right, it is quite manageable for me to think through. It'll take 5 minutes for me to understand what's going on and get a sense of what the model is doing. This tree on the left here, it may be more predictive and more powerful, but I don't think there's any amount of time I could spend to ever actually understand what's going on and gain some intuition about the model's behavior. It's just simply too complex for me to think through. And then after simulatability, There's algorithmic types of transparency. So you're probably very familiar with some of the guarantees that you could get with, for example, linear regression, where you're guaranteed that the input variables will be related linearly, and the whole problem is conforms to a linear solution. Other softer methods might be, rather than specifying a model form, you might at least gain guarantees about the uniqueness of the solution, or similar types of softer guarantees. And like I said, all of these things really do tend to really actually sacrifice predictive power, which is usually, in our opinion, not too worth it. After that, we have post hoc types of interpretability. Now, this is interpretability that does not sacrifice any modeling power, because you don't even think about it until after your model is trained, right? You're simply trying to query your trained model and have it explain its decisions through rigorous interrogation. But as a result of that, it's frankly just not as human friendly, right? Because the model has not been designed with that in mind. So in order to deal with this, often this type of interpretability seeks to explain individual predictions rather than the overall model, in part because that's just easier, but also because the model tends to be very complex and with very many facets to its decisions, making that frankly quite hard to think through. As we touched on earlier, there are two levels to interpretability: global, which refers to the model's general behavior, and local, which refers to explanations about specific predictions made by the model. Now, a couple examples for global would be solution form, such as specifying a priori that it should be linear or parabolic. There's feature importance. There's a global surrogate, which is actually training an interpretable model on the predictions of your uninterpretable model to get some sort of idea on what your model is doing. On the local side, we have things like saliency maps, Lime, SHAP, and by example. Now, I'd like to talk a little bit about the trade-offs between a few of the more common methods, so you have some rule of thumbs as to what you should use. First off, and most common really, is the saliency map. It's fast, it's visual, it's nice to see, it's very easy to do, and it's been around for a long time, so people love it, but honestly, do not use this. It's very fragile. It's small shifts to the input distribution can easily destroy this method. It's very sensitive to adversarial attacks and very sensitive to human bias. So I really do not recommend you use that. Next up is permutation feature importance, which is great. It's really easy to evaluate, really easy to interpret, and it takes into account the dependencies between your features, which is wonderful, because that's honestly why we're using these machine learning methods in the first place, right? We care about the nonlinear relationships between things. And then finally, it's global, which is a huge benefit as well. But you know what? This does break down with highly correlated variables, or even with nonlinearly related variables, which is frankly a very tough thing to take care of or to fix, and hence often I still would not recommend doing this as your final cut. After that, and perhaps most recently, is SHAP, which is a wonderful new technique, and it conveys many theoretical guarantees. It probably is one of the only methods that does, which makes it very suitable for regulatory situations, and it gives you a global and local explanation in one unified framework, which is wonderful. And it's extremely fast for tree-based models. But the downside is, in general, outside of tree-based models, it's very slow. And if you want to compute a version of this that has feature dependence, well, not only is it extremely slow, the features created are often very unintuitive, and if the explanations are unintuitive, what was the point of getting any type of interpretability in the first place? You still need to understand it. And then finally, and this is our preferred method, would be the by example strategy. There's many methods for doing this. It's very helpful for debugging your model and improving your model. It's generalizable and can even help you to find gaps in your data, places where you need to get more data. But it is slow, It really is very, very slow to calculate. And since it's really just giving you samples or examples of related things to its prediction, it's actually not a true explanation. It's relying on you as a human to come up with a reason why, or disentangle why the model thought these samples were similar. I'd like to talk a little bit more about the explanation by example, so you have something hopefully new in your toolbox at the end of this. Here on the left, we have a simple neural network. Input to it is some sort of molecular descriptors, perhaps QSAR data or something else. Now in the middle, we have our so-called learned representation, the hidden layer of the neural network. And then finally, our prediction endpoints. Now, let's say we have fed in some molecule and we want to know why it made the prediction it did. Well, what we can do is simply get the learned representation of that molecule and then do a nearest neighbor search of that representation versus the representation of all the other molecules in our data set to figure out, all right, what molecules does our model think are very similar? And this is often a nice way to get intuition as to why, but also to discover new things about the core fundamental phenomena. Now, that naive approach is good, but we've found in practice some slightly better strategies, since the nearest neighbors really can only show you what's in your data set, and the neighbors may be far, for example. And it really only gives you one or two different ideas, which may be not representative about why your model made its decision. So what we like is a variational autoencoder approach. So on the left, we have a very typical VAE. The input is our molecular descriptors, but the output, once again, is the molecular descriptors. And in the middle, we have this bottleneck layer where we are forcing the model to learn a representation that is actually Gaussian. So we can sample from this representation actually, and from the latent space to generate fake molecules. Now, we share the weights with another model, our predictive model. And so the first layer of the predictive model is actually a generative embedding. And then finally, we use that learned representation to help for predicting our endpoints. If it's not quite powerful enough, what you might do is throw in a little tiny auxiliary layer here to help improve your predictive power. Now, what you can do with this is once you have a prediction, instead of searching for a nearest neighbor, you just take your representation of that molecule and generate a new molecule in all of the different cardinal directions away from your current molecule to get a sense of multiple different reasons or different features that your model is taking into consideration in thinking about this specific molecule. I hope you walk away from this today excited about interpretability, not just for increasing adoption and trust of your great models, but actually to help you. There are so many bench scientists out there who are not modelers but have amazing insight into the problems that we're trying to model, but they don't have an easy way to work with us on improving our models. Opening up the interpretable box really provides a platform for everybody to work together on this and improve the quality of our models and the insights gained from them. Additionally, there are so many local tools that are coming out and they're getting better, but they can still be misleading. You do need to know how they work, and you do need to make sure that you are rigorous in the way that you use them so as you don't provide too many biases. And finally, global interpretations, despite being very nice to see, often come at a huge performance cost. Thank you, and if you have any more questions, please feel free to reach out directly.